Hello, everyone, and welcome to today's presentation. I'm Tammy Diedrich, the managing editor of IBM Systems Magazine, and I'm the moderator for this event. Today's webinar is sponsored by MVS Solutions and is titled Capping Capacity versus Demand. Our featured speakers today are John Baker and Selby Shanley. John Baker is a ZOS performance specialist with more than 20 years of experience as a user and consultant. He has assisted many of the world's largest data center customers with their ZOS performance challenges. John has held subject area chair positions with CMG and is a popular speaker at CMG, Share, and IBM conferences. Selby Shanley is a principal designer and developer of ThruPut Manager Automation Edition and is an MVS Solutions resident subject matter expert. Selby is steeped in mainframe technology and is well known globally as a ZOS, JES2, and WLM expert. In this webinar, John and Selby will discuss the challenges ZOS customers are facing with today's environment of capacity constraints. And they'll share a novel approach to automatically control demand of low priority work and ensure peak performance of critical applications, all demonstrated with real-world enterprise data and experiences. Following the presentation, we'll have a Q&A period, so please feel free to enter your questions in the question panel on your screen anytime during the presentation. Now, without further ado, thanks again for joining us today. And John, I'll turn the presentation over to you.
Thank you, Tammy. Thank you, everyone, for attending today. We have a very focused agenda, so let's just get right to it. The theme of our session today is automation, and how that automation is delivered with ThruPut Manager Automation Edition, or TMAE. We will discuss capping capacity in the traditional sense as it's done today. Then we'll talk about capping demand, an innovative technique we've developed with TMAE to directly reduce monthly software costs while maintaining performance for your key applications. Finally, we'll talk about automating workload management, a necessary step to enable capping demand. Capacity management and workload management are key techniques that have been in the data center for years. Our position is that these functions need to be automated. While anything can be accomplished with an army of people, machines, and money, automation is the most effective and efficient technique to run a data center today. You'll see these charts again later in our presentation. The chart in the top left illustrates how automated capacity management can lower software costs. The chart in the bottom right shows how automated workload management can improve performance by managing utilization and balancing workloads. Why do data centers cap anyway? Deciding to use capping means making a conscious decision to lower your capacity levels, thus increasing your utilization levels. It seems counterintuitive to performance. Of course, this is why. Software is the largest operating expense in the data center. While subcapacity pricing allows billing based on peak consumption, running without caps means a spike in the rolling 4-hour average can lead to unacceptably high software bills. Caps provide the ability to control this cost, but at a price to performance. Caps are also referred to as capacity limits. As I mentioned, their primary purpose is to control monthly software charges by limiting the rolling 4-hour average. Hard caps limit application CPU consumption to the capped level at all times. This means the rolling 4-hour average can never exceed the cap limit. Soft caps only limit application consumption when the rolling 4-hour average exceeds the cap level. This is what a hard cap looks like. Neither the application demand nor the rolling 4-hour average is ever allowed to exceed the set limit. It's just like having a smaller machine. This ensures very consistent software bills, but can be rather unforgiving to application performance. This is what soft caps look like. The application demand is freely allowed to exceed the cap limit because the rolling 4-hour average, as shown with the red line, does not exceed the limit. As you can see, this option provides much more flexibility to application performance. When the rolling 4-hour average does exceed the cap limit, applications are immediately affected. When this occurs, the LPAR, or group of LPARs, is capped by Prism. CPU resources are only provided to the LPAR at a rate that does not exceed the capacity limit, regardless of the actual application demand. The effect is very much as if the applications are suddenly running on a smaller machine. Further, the capping will remain in place until the rolling 4-hour average is back below the capacity limit. In this case, the effect remained for 3 hours. So what do we do when cap limits are exceeded? Our traditional manual methods are to monitor and react to changes as best we can. We cancel jobs, adjust priorities, and do our best to help our applications continue to perform in a more constrained environment. It requires a lot of expert staff and still can't be performed at machine speed. Availability is usually job one in a mainframe environment. So often, we simply resort to raising the cap. While this provides a positive effect on our applications, it provides a negative effect on our software bill. There's really no point in putting the cap back down, as the software bill is based on the highest peak. Recalling our description of hitting the wall, when the rolling 4-hour average hits the capacity limit, the entire LPAR is capped, potentially affecting all applications on the LPAR. Rather than allow this to occur, TMAE allows you to only cap specified batch workloads. Further, TMAE takes a soft hammer approach by gradually reducing or deferring the CPU consumption of the batch that you designate before you hit the wall. Many shops are under the mistaken impression that batch does not impact their peaks because it runs at lower priority or it runs at night. It's simply not true. Firstly, bear in mind that all workloads contribute to the rolling 4-hour average, regardless of priority. A CPU second is a CPU second. Secondly, consider the following chart. This chart was generated from actual customer data and only reflects the day shift. While online is certainly the dominant contributor, note that batch makes up a significant portion of the rolling 4-hour average. Even a modest reduction in batch consumption during these peaks can yield significant software savings while maintaining performance of your key workloads. Now, Selby's going to go into a little more detail about how TMAE allows you to lower your software costs by capping demand.
In order to cap demand at the right times, TMAE has to understand the environment and be aware of any changes that may occur. Of course, TMAE determines if there are any defined capacity or LPAR group limits set by the installation and will detect any changes made to these limits. It also tracks the current rolling 4-hour average CPU usage for each LPAR and the current CPU demand. It's important to keep current demand in mind when making decisions on whether or not certain workloads should be increased. In order to have a full picture, TMAE also tracks the overall CPU consumption of the KEK and each LPAR in the KEK. High CPU consumption by one or more LPARs can affect CPU availability for other LPARs. TMAE monitors batch workload performance to avoid overloading, leading to poor overall performance and delays. This is particularly important when capping demand, so that the workload being capped still performs as well as possible given that it is being constrained. TMAE caps the batch workloads chosen by the installation in 3 phases. First of all, as the rolling 4-hour average increases and approaches the limits set by defined capacity or LPAR group limit, TMAE automatically starts restricting the CPU consumption by these workloads. It does this in 5 gradual steps. The idea is to slowly shrink usage and avoid hitting the limit with very high CPU consumption. We usually refer to this as hitting the wall. When you become soft-capped at high rates of CPU utilization, this sudden drop in CPU availability can significantly affect performance. And when this happens, this usually causes installations to immediately increase their limits and their software bills. By taking action in stages before the limit is reached, TMAE makes capping manageable and eliminates the negative performance effects. Then, while soft capping is occurring, TMAE continues to constrain the lower priority batch workloads to the maximum extent specified by the installation, reducing the overall CPU demand in each affected LPAR. This leaves more cycles available for high priority workloads such as online, even if the high and low priority work are on different LPARs. Once the peak passes, the LPAR is no longer being capped, and overall consumption begins to come down. TMAE starts to smoothly remove the constraints on the affected batch workloads, gradually allowing more access to CPU, reversing the 5 steps that I just talked about. The goal is to automatically get as much of the deferred workload running as quickly as possible, as long as the rolling 4-hour average is not increased, a difficult task without automation. Gradually, TMAE starts to run the deferred jobs. As long as the rolling 4-hour average does not increase, the constraints will be relaxed further, and more of the deferred batch workload will be allowed to run. TMAE also makes sure that the deferred work is selected at a rate that does not overload the LPAR. TMAE makes it possible to live not only with the caps you may have currently implemented, but to reduce them further while still protecting the performance of your high-priority applications. Lower cap values translate directly into lower software bills every month going forward. Now, here's a couple of examples to show how this all works. Here's an example of an LPAR group with 2 LPARs, LPAR 1 and LPAR 2, with a mix of online and batch load. On the left, before using TMAE, we see that on LPAR 1, online and batch are both contributing 600 MSUs per hour to the peak rolling 4-hour average. On LPAR 2, online contributes 700 MSUs per hour and batch 300. The total peak rolling 4-hour average is 2,200 MSUs per hour. On the right, after implementing TMAE, the installation decides that 25% of their batch should be eligible to be deferred. The results? The online usage remains the same, while the batch is smaller for a new total peak rolling 4-hour average of 1,975 MSUs per hour, a saving of 225 MSUs per hour. So the LPAR group limit can be reduced by 225 MSUs per hour without affecting online performance. In this second example, we have a different configuration, an LPAR group with 2 LPARs, 3 and 4, one of which, LPAR 3, has mostly online, and a small amount of high-priority batch that must run on that LPAR, and another, LPAR 4, that runs entirely batch load. On the left, before TMAE, the peak rolling 4-hour average for this LPAR group was 1,850 MSUs per hour. Now, this installation wants to reduce their peak monthly rolling 4-hour average, but they have also reached a point where their online applications are going to need more CPU to handle an expected increase in transaction volume due to the introduction of a new application. These are usually conflicting goals. However, After implementing TMAE, the installation identifies 300 MSUs of batch workload on LPAR 4 that can be deferred during peak times. They decide to reduce their LPAR group limit by 200 MSUs per hour and let the online work on LPAR 3 consume an additional 100 MSUs per hour. Note that the batch on LPAR 3 is all high priority, so they left it alone. Their online applications got the capacity boost they needed, and they still reduced their peak monthly rolling 4-hour average. Here's a graph created from actual data from a large TMAE installation. On it, you can see the rolling 4-hour average, the CPU utilization, and the horizontal line is the limit. In this case, the installation is using LPAR group limits. Notice how the rolling 4-hour average line gradually flattens until it just barely hits the LPAR group limit. This is TMAE in action, reducing the demand and the growth in the rolling 4-hour average so that the effects of capping are minimized. This customer was able to reduce their limits and realize 7-figure annual savings. So let's look at some typical savings. This chart shows the expected savings for 3 different installations. For each of these, the contribution of all batch workloads to the overall peak rolling 4-hour average was determined, and then assuming that 25% of that is lower priority and deferrable, the potential savings were calculated. For this, we used a rate of $300 per MSU per hour, which is typical for a large installation with the usual IBM software set. Smaller installations will not save quite as many MSUs, but in some cases their incremental rate is very much higher, so the savings can still be substantial. Some installations' current annual savings exceed the $1.3 million shown on the chart. Now, John is going to talk to you about what we need to make this happen.
It's clear that capping demand is the key to lower software costs while protecting key applications. To enable the capping demand of our applications, we first need to take control of our applications with automation. Changes in system utilization and workload demand happen at machine speeds. We need to anticipate and react at machine speeds as well. This means dynamically tracking and managing utilization and automatically balancing workloads across the available resources. Here we have an overutilized highway. The design doesn't prevent more cars from coming on the road, even as the average speed of all the cars approaches 0. The result is many cars on the road, but no one getting to their destination within the expected time. The same principles hold true in a computer system. If additional workloads are continually added to the system, even as utilization reaches critical levels, everything waits longer. Some users may have a comfortable feeling since they see their job has started, but like the cars on the highway, the job is not going anywhere very fast. You can see from this queuing graph that at very high levels of utilization, the total elapsed time becomes 10 or 20 times longer. The CPU is working just as fast, but the wait time to access the CPU increases exponentially. As utilization approaches 100%, the wait time increases to intolerable levels, just like gridlock on the highway. The key to peak throughput is to constantly manage the workload distribution against the rapidly changing utilization to maintain just the right amount of load. Selby's going to explain how TMAE accomplishes this automatically.
To avoid overloading, TMAE only adds batch load when and where it makes sense. LPARs must have available capacity. That means either the LPARs are not using up their CPU entitlement by weight, or there are still unused CPU cycles on the CAC of which the LPAR is able to take advantage. The service class in which a job will run must be performing well to avoid unproductive overloading, because everything works better when you avoid overloading. It's not important when a job starts. It's when it ends that matters. This is even truer with production applications where one or more jobs may be dependent on the completion of another. Jobs end sooner in a TMAE-managed environment. And we did a benchmark that shows this. We ran over 1,000 jobs being submitted over several hours. These jobs had a mix of CPU and I/O load and were run in WLM batch initiators and under TMAE. There were no job dependencies. Of course, the two environments were identical in every way: hardware, software, and service class definitions. No other work was running on the KEC. The result? TMAE ran far fewer jobs at once, starting many fewer initiators, but completed much more work. Here's the graph of the benchmark results. You can see that the work ran for hours. WLM started 300 initiators, while TMAE automatically started only 25 initiators. As you can see from the graph, after over 8 hours, TMAE had completed 200 more jobs. The only reason it didn't get higher is that we stopped submitting work. And these results would be even more dramatic with workloads that make use of job dependencies. Many installations use manually controlled just-to initiators. In that environment, you will often find that the machine either is overloaded or underutilized, since it's just not possible to be as effective manually as automation that is constantly monitoring the environment and making instant decisions. Sometimes less is more. By avoiding overloading, TMAE gets more batch jobs done faster. And systems are much more prone to overloading when capped, which is why automation is so important when managing demand in a soft-capped environment. Balance is also important, and John's got a good example.
I think it's safe to say this load is imbalanced. As we mentioned previously, the other key factors in effective automated workload management is balance. As we demonstrated with utilization, a system running at 100% is spending more time waiting than doing productive work. In the example given here, even though the system at 60% will provide slightly better service than the systems at 80%, the exponential delays experienced by the system at 100% will more than wipe out those gains. The facts are simple. In order to achieve peak performance, workloads must be balanced across the available resources. As with utilization, workload demands change too rapidly to manage manually. This is another automated function of TMAE.
In order to balance batch workloads automatically, TMAE makes sure it is aware of the performance and capacity of the entire environment. It tracks the utilization of all LPARs and the required system and resource affinities of all batch workloads. The installation-specified business priorities are defined to TMAE so that it always selects the most urgent job. Workload is balanced automatically because TMAE controls the number of initiators on each system and dynamically spreads the workload across all members of the JESPLEX. TMAE does workload balancing right. Balancing is not simply making sure the same number of jobs are running on each system. Balancing means that each system in the JESPLEX runs the right amount of batch workload for the current conditions on each system while still respecting any specific system affinity and resource requirements of individual batch jobs. TMAE considers the actual activity on each LPAR and reevaluates KEC, LPAR, and service class performance every 10 seconds so it can respond to environments that can and do change very rapidly. Only automation can do this. TMAE avoids overloading by rebalancing the batch workload as CPU demand and availability change. Capacity can change too, due to capacity on demand, LPAR weight changes, and of course our old friend soft capping, which can cause the available capacity to be suddenly reduced. By balancing batch workload intelligently, TMAE delivers increased throughput with proper use of existing resources. John?
Automation is simply no longer an option in data centers today. Capacity and workload managers need to harness this technology to control costs while maximizing performance. Automated workload management provides the necessary controls to maximize throughput by managing utilization and balance. This control enables the data center to cap demand, the only way to safely reduce cap levels and lower software costs. I'm going to pass the mic back to IBM at this point, and we'd be happy to take your questions.
Great, thank you. So we will take some questions now. We have plenty of time, so if you have a question, please enter it in the Q&A panel on the right side of your screen and send it in. Also, if you could note, we are popping up a little poll on the bottom right of your screen. We'd appreciate it if you'd answer those questions before you leave. Okay, first question. We are already using LPAR groups for capping. How can ThruPut Manager help us further?
I appear to be muted. Apologies. Selby, do you want to take that one?
Yeah, we can. We help because we actually cap demand. So if you already have an LPAR group, as we showed in the two examples, which were both of installations that had LPAR groups, by capping demand, you can reduce that and or you can reallocate those cycles elsewhere. So the savings can be quite significant because the alternative, for example, in example 2, would have been that the installation would have actually had to increase their cap to accommodate the new online application.
Yeah, if you're running caps today, essentially, it's going to ensure that you don't spend more than your workloads are demanding, but it's not taking into account what the priorities of your workloads are. You could have a test batch. You could even have a runaway looping program that will drive up your rolling 4-hour average, and the caps are going to allow that. You really need to control your demand if you want to lower those caps significantly.
So this question seems to dovetail right into that. How can I determine the contribution of my batch workloads to my peak rolling 4-hour average?
That's a great question. I'll take that one. It's not easy, I can tell you that, but it absolutely can be done. The rolling 4-hour average, as many of you may know, in performance and capacity, is tracked in your SMF Type 70 records, but it's not broken down into the distribution of your workloads. We have created an MSU measurement tool here at MVS Solutions that will analyze the contribution of your batch workloads to the rolling 4-hour average so you can estimate exactly how much you can potentially save.
Okay, so jumping back one question, can you define an LPAR group? Is this grouped in TMAE?
Yes, it's the standard IBM LPAR group, the one that you defined today. TMAE detects that you have defined it. It knows what the limit is, and it uses that as that's the goal.
yeah, essentially whatever limit you've set on one or more LPARs, TMAE would be aware of that and will manage against that limit.
It also is aware of defined capacity and will work in a situation where you have defined a defined capacity for a given LPAR that is also a member of the LPAR group, and TMAE will sort out all those limits, and it knows how much the LPAR can actually have.
How does TMAE handle data contention?
Go ahead, Selby.
Okay, there's a component of TMAE that handles, I assume what is meant by this is data set contention, and it automatically makes sure that jobs just don't hang around initiators waiting for data sets that are currently enqueued by other jobs. It even actually tracks the time that the job is in the queue waiting to get access to the data sets and reports that on in the job system messages. So that's all handled automatically, and they don't hang around tying up initiators.
All right, does TMAE have any value in a monoplex?
Absolutely. TMAE can work within an individual LPAR. It's aware of the operating system where it's installed. If there are others, it would be aware of those as well, but certainly in a monoplex where you only have one system, that'll work just fine.
The other thing I would comment on that and add to it is that an LPAR group can span JESplexes and monoplexes and sysplexes, so that with TMAE running on each of those machines, they will still adjust based on what is happening in the entire group. And TMAE will still be aware of the entire KEK utilization, regardless of whether those other LPARs are in the same JESplex or even in the same sysplex.
All right, how does TMAE handle user jobs peaking, which may have been submitted with a high priority class by mistake?
Well, TMAE analyzes every single job that's submitted, whether it comes from the job scheduler or whether it's submitted by a user. You have the ability, we haven't gone into a lot of those details here, but you have the ability as the administrator of TMAE to adjust jobs regardless of what the user may have submitted. You're not dependent on what they code in their JCL, essentially. Selby, you want to expand?
Yeah, you can override that, and there's an enormous amount of flexibility here. And as with any if you have a runaway job, for example, presumably batch will be lower regardless of the service class that it ends up in. And TMAE very much controls where the jobs end up. So as John said, you can override and control what the users can and can't do and decide whether this particular user has made a mistake. But even if batch starts to really increase because you have a looping job, TMAE is aware of that and will make sure that it doesn't start loading even more batch into the system, thereby helping to protect your online.
All right, how does TMAE handle runaway DDF and trainids, or is TMAE only for batch?
TMAE handles batch jobs and controls batch jobs. However, if you have something runaway, then TMAE will start shutting down the batch workload so that you still have more cycles left for your online.
All right. Isn't the rolling 4-hour average in type 70s the hardware and not the software average?
Well, go ahead, Selby. Or you want me to?
It's what's used for the software billing, and they're usually referred to as software SUs. The millions of service unit average, the rolling 4-hour averages for each LPAR in the SMF Type 70 records, is indeed what is done. Now, that being said, we're completely insensitive to the SMF records. TMAE determines the rolling 4-hour average on its own. because it needs it far more often than an RMF interval. But that is the number, and that is the one in the Type 70 is the one that this IBM subcapacity reporting tool uses to generate your usage report at the end of every month.
Right. Does it work when the when the rolling 4-hour peak is in the night with only batch workloads?
Yes, absolutely. Because then if you've identified the batch workload that is to be deferred, it simply kicks in and lowers it. Absolutely. And so it will run a bit later after the peak has gone down. And it's important to note that the peak of usage may not be the peak of your rolling 4-hour average. Those are sometimes not at the same time. But it's very much geared to controlling the rolling 4-hour average. And so therefore, when it sees that coming in, it will start to take those steps that the installation specifies to start constraining the batch load that doesn't have to run at peak. Because yes, some installations, their peak rolling 4-hour average is in the middle of the night.
All right. Billing happens on a machine level, but capping happens at an LPAR level. If there's a spike in some other LPAR, will it affect the 4-hour rolling average?
If you have an LPAR group, that's how it can tell. If those are in the same LPAR group, then you see that the group as a whole has spiked. And that's where you get things like the second example we had, where you can start reducing the load on one LPAR in order to benefit another.
Yeah, as Sylvie said, essentially your bill is based on the machine total from each LPARs, but because TMAE is aware of the workload and utilization and MSU consumption on all of the LPARs on the machine, and as you mentioned, that also can span sysplex boundaries. There's no problem there. Exactly in the example that was shown, we can reduce the workload on a given LPAR to provide resources to another LPAR.
All right, great. Another question here. If most of our software license agreements are based on MIPS with no capacity pricing, would capping still save us money?
Well, we would highly recommend all shops to take a close look at the subcapacity pricing option. It really does allow you to pay for what you're consuming as opposed to paying for the entire capacity of the machine. But certainly all of the TMAE functions that we've described in terms of improving throughput and workload balance and managing utilizations, those will still work. And as Sylvie mentioned, while we're certainly aware of any cap level that may or may not be set, if you choose to run without those, Throughput Manager is still going to improve your throughput.
There's one other thing, too, that if you, for some reason, you are using subcapacity pricing, but you just don't want to have a cap of any kind, you can specify a limit to Throughput Manager AE that it will then work to in place of any defined capacity for an individual LPAR.
All right. Do you have some sort of tool we can run that will show the change TMAE will have within an environment, like, for example, the potential cost savings?
Yeah, absolutely. As I touched on earlier, what we call the MSU analysis tool, we can analyze your SMF data, and it's the same data that is sent to IBM to calculate your monthly bill. We can analyze that data. It will identify a number of the peak rolling 4-hour averages within the month, so not just the individual peak, but actually the top 25 or 50 peaks, and the batch contribution to that. So you can very easily estimate the actual potential savings by running TMAE, just by running that tool.
Okay, if multiple service classes are missing their goals, does TMAE consider the service class importance or velocity goals in its prioritization of what gets started so that higher priority work gets started ahead of lower priority work?
Yes, it does. It looks to see, it's primarily concerned, by the way, of when it looks at the goals of how is it doing. And it wants to make sure, not only from the goals, but other information about the service class performance, that the service class is not becoming overloaded. Because the last thing you need, as I think John's picture of the highway shows, is to add more load to a service class that is not getting CPU. And ThruPut Manager AE is very aware of how much CPU is available to every service class and manages accordingly and makes the selection decisions accordingly. In general, what seems to happen in machines is that the high priority service classes, by their nature, always have CPU available to them, or almost always. And so jobs will tend to be selected and start in those classes. The lower ones, when things get congested in the system, AE will back off if it sees that those service classes simply aren't getting the service they need, just to avoid the overload, which just slows everything down.
All right. I'm assuming a rogue CICX or KIX transaction could potentially throttle all my batch regardless of their importance. How does TMAE deal with that?
I think it would be unlikely for that to happen because of multiple engines, because of multiple processes. When something goes rogue, it's usually, and it's looping, it's usually only taking one processor. So there's still CPU left. If you manage to get a whole bunch of them and the high priority locked out everything, then yes, you would. But I would also add the following, that even without TMAE, you would have the situation where the lower importance work wouldn't get any cycles at all. So in general, though, I think by and large they won't do that. It will affect the amount of CPU, and therefore TMAE may cut back on certainly the lower priority batch at that point until the situation is resolved, because once again, there's no point in overloading if the SRM is not going to give it the cycles.
All right. Can you change the TMAE prioritizations by shift?
Yes, there is a capability of specifying. You specify a lot of this stuff in a policy, and the policy can have different modes, and you can issue a command and switch to a different set of definitions.
Essentially, within the policy, just like Workload Manager, we have levels of importance and we have service groups. And yes, you can, as Selby said, you can have a night shift and a day shift or a weekend shift and so on.
All right. How does TMAE have the ability to prioritize the batch workloads to ensure the high priority batch enters the queue first?
The installation defines, you usually start off with the job classes you have now, but they can use a lot more than that. But simplistically, we'll start with the job classes, and they can say which ones are more important. They give us an importance. They can also say that things of this importance get run in a certain service class, and also they can give us their SLAs. You define your SLAs to us, your service level agreements. How soon should these jobs be started? What's your target? What's acceptable? When does this become critical? Some things are not important enough to become critical. And TMAE will manage the queue accordingly. And that's how it knows what's most important. Something that is not going to meet its SLAs suddenly becomes very important. And then it takes into account how important that one piece of work is relative to any other piece of work.
Okay, I have a couple of version compatibility questions. One is, what levels of ZOS does this support?
Any level of ZOS that is currently supported by IBM, including, of course, version 2, release 1.
And is it compatible with all versions of JES?
It works with just 2.
Okay.
Just to add to that compatibility, you'll see on the screen here, because we are an IBM development partner, one of the great parts is we are always ready, at release time for the next code release. So as as Selby said, ZOS 2.1, which many of you may be migrating or have already migrated to, we were ready for that before it came out the door.
All right. Is TMAE limiting workloads all the time or only when the rolling 4 hour is approaching GCL limit?
It is not doing it all the time. These constraints only take effect at points that you select. Usually it's when you get about 90% of the way, or even 80% of the way. It's up to you. There's those 5 steps that I referred to in the presentation. And you can say, well, I want you to constrain it a little bit because, we've got to 85% of the goal. And now you get to 90%. Okay, I'd like you to constrain it a bit more. And this goes on. There's 5 steps. The 5th step, of course, is you're at the limit. And so gradually things get backed off. And then that happens in reverse. Once the limit is passed, the rolling 4-hour average is coming down, and it starts work up, monitoring all the time to make sure it just doesn't push it up into capping again.
I'd just add to that, as you said, we're only going to take these actions when we're in a capping environment. When we're nowhere near the cap, TMAE actually increases your throughput, as we showed with the benchmark example against the WLM hits. The idea is actually to move work through the system faster than it is today without TMAE, and then only implement these controls as you have designed in the policy as you approach the group limits.
All right. Does TMAE tap into scheduling tools like CA7, TWS, Control-M to understand where a job is within its schedule?
Selby, you want to talk about AE+?
I guess we can talk about AE+ a little. We have another level of TMAE called TMAE+, which does those sort of things and provides a wealth of information that is really beyond the scope of this webinar on for CA7 installations, and where it is aware and it knows the history and it calculates critical paths and does all the good things that all the production control people would want, helps them identify problem jobs, etc. However, I must say that the TMAE that we've talked about today can handle jobs from any job scheduler, or you don't have to have a job scheduler.
All right, great. Well, thank you so much, John and Selby, for sharing your expertise with us today, and thank you everyone who is attending for sending in such great questions, and so many of them. We appreciate it. So just a note that we will be sending out a link later this week to early next week, to a recording of today's presentation to everyone who's on the call, as well as to anyone who registered for the event, but for whatever reason couldn't make it. So that concludes our webinar. I want to thank everyone for attending, and have a great day.